one of the beauties of this technology is, since we're talking about, planar capacitance, where the whole sheet, the whole power ground plane becomes acting like one big capacitor, you don't have to basically physically make cutouts and design little discrete capacitors. It's not like the buried resistor you mentioned earlier, where you have to physically place a component. The whole power ground plane becomes one big capacitor. So from that standpoint, there's really not a change to the layout, what you need to do. But what it does do is it frees up all that space that you would have taken up with decoupling capacitors. And usually you're placing your decoupling capacitors close to your chip package, which is the most expensive real estate on the board. And that's where the highest routing density is. So if you get rid of those decoupling capacitors, that gives you, it frees up a lot of real estate. The one thing you do have to do, though, is that because it only works when the power and ground planes are together, there's a number of designs out there that basically have your power plane, your two signal layers, and then a ground plane. Yeah. And so the power and ground plane are separated by all this dielectric. And so sometimes we had to work on a design a few times where we actually put in a redundant ground plane, just so that we could have that to create that decoupling layer in there. So that's a consideration. You may have to take a 14-layer board. We went on a 14-layer board up to a 16-layer board to do that. Again, it added some costs, but they did see the performance they were expecting out of that.
I see.
So that's probably the biggest consideration, is if you don't typically put your power and ground planes together, you may have to do something like that. And the other thing too is that there are, when it comes to design, fortunately, over the years, when it comes to design tools, I think we all agree that lots of times the tools come after the technology, because you want to see if it's a real technology or not. If the design company is going to invest the resource, especially for simulations and things of that nature. Well, fortunately, this technology has been around a while, that there's really good simulation tools. So what you would typically do is take your stack up and you would substitute the dielectric parameters, the thickness, dielectric constant of the power ground planes, and you could simulate and see how many decoupling capacitors you really do need at that point. And it's amazing that you can eliminate 90+% of the decoupling capacitors that you think you need. If you added up all the capacitance of these decoupling capacitors and you looked at the capacitance in that power ground plane, you would say, wait a second, there's only 5% of the total capacitance. But again, it's not about capacitance at the higher frequencies you're decoupling, it's about inductance. And at higher frequencies, those little capacitors really act more like inductors. So that's what the real secret is about this technology. That's why I tell people it's kind of a misnomer. We call it embedded capacitance, and it's really more about, reducing inductance.